I'm going to talk about is a regime which is belongs to the broad area of what the talks have been about this morning, which is the area of active matter. But I'll talk about a regime which is far away from what Ludovic talked about in the sense of extremely dense active matter where you see glassy behavior and other interesting things. What I'll be talking about is actually a collection of what happens when you look at collection of microorganisms which swim. So the self-propulsion part is identical to that of Ludwig's talk. However, I'll be working at concentrations which are much smaller, right? So you won't have all that interesting glassy dynamics and whatnot, but you still have many other effects which we'll see in a moment. And what I will also like to talk about is a system where walls matter. So I'll try to talk about an experimental system where you have walls, and I will show that the presence of walls have a crucial impact on the physics that you observe, right? So that would be in some sense the broad idea of this talk, and this work was done in collaboration with Martin Bayes, who is an applied mathematician doing experiments on these systems at University of York and me, and the paper would be soon out this month. So let's go ahead. So what is bioconvection? It's a collective behavior of gyrotactic organisms. So what is the example of a gyrotactic organism? It's algae, maybe chlamydomonas. And what you then do is you take this algae, put it in a beaker, right, and wait. And what you start to see is these spectacular patterns which resemble, if you have seen any videos on fluid dynamics, thermal convection. Okay, and the question is, why does this happen? Can we understand it? And you know, there are all the kind of patterns which are similar to cell-like structures which one observes in thermal convection, which is observed over here. And you know, there are nice review articles, and actually this subject predates active matter. So the first papers on these subjects came out in 1980s. I think that's the time where the word active matter itself wasn't coined, and people were already looking at the collective behavior of microorganisms, trying to understand theoretically how could we address this problem. And what I'll again show is that, you know, with the insights that one has gained or the methodologies that have been developed in active matter, what all you can do with this kind of things. So let's go ahead and let's first try to understand the organism itself, which is making these kind of patterns when you, instead of working with just one organism, look at the collection of organisms, right? So our hero of the story is this guy algae, which is a chlamydomonas. Now what is interesting about it is that it senses gravity. So it likes to swim in the direction opposite to the gravity. So it likes to swim upwards. Second is the following, that it's bottom heavy. So its center of mass, it's nearly spherical, its center of mass and center of geometry are not at the same point. What does that do? That if you put this organism in a shear flow like so, then the flow will try to rotate the organism, but because it's bottom heavy, there is a torque which is acting on the organism, which will try to realign it, right? This idea of torques balancing gravitational or swimming of the organisms upward is called gyrotaxis, all right? And what then you can do is you can write a torque balance. So that what is the total torque on this body? Remember, we are working, these organisms are microorganisms, so Reynolds number is very small, inertia doesn't matter. So the total torque, whatever is there, is 0. So what is the total torque? There's a drag term, which is standard drag term. Curl of u is the velocity of whatever flow you have. Omega is the rotational velocity of the organism itself, and this is the torque. Mg is the direction of the gravity. This is the distance of the center of L is the distance of the center of geometry to the center of mass of the system, right? So that's the net torque on the system. You can solve for it, get an equation for omega, or much more easier, what you can define is an orientation axis which points along the swimming direction. Then you take this, the torque balance equation, do a cross product with the orientation vector, you get a time evolution equation of how does the orientation vector changes in time. That's fairly trivial. And then you have something very interesting. There are two features which you straight away start to appreciate. One is that the organism, as expected, is trying to align itself in the direction of gravity. And the second thing is that because there is a vorticity present, it's trying to reorient. Now, because this organism is nearly spherical, we don't have any contributions from the elongation strains present in the system. If you had an organism which was elongated, like a bacteria, then you would have additional couplings coming like lambda s dot p, where s is the rate of strain tensor, which fortunately we need not worry about in this for this simple organism. And just to again keep things clear, it's important to know what are the numbers that you're working with. The size of the organisms, and when I say size, I imply the diameter of this organism is around 10 micrometers. The typical speeds can vary from 15 to 60 micrometers per second. The offset of the center of geometry to the center of mass is around 0.1 micrometer, and that offset is good enough to now we'll see do very interesting behaviors. But remember, at the scale of the organism, okay, the Reynolds number, which tells you what is the ratio of the inertial forces to viscous forces, is extremely small. So for a single organism, you are really still thinking of it in the Stokesian swimmer regime, right? And another thing to keep in mind is that these organisms are slightly heavier than water. So if they were not to swim, they would sail downwards, all right? And because they can swim, they can also stir the fluid. Now, for the people who are experts in active matter, they would realize that this is immediately, these are contractile swimmers. So they swim and generate the flows. So now let's go ahead and let's ask what is it that we expect. So now that we understand what does a single organism do, so let's revise. Swims upwards because center of gravity is different than center of mass, has torques slightly heavier than water, would settle, and then swims and generate flows also. All right, great. Then what happens if you take collection of such organisms? Should one study it? Turns out that these organisms or algae are extremely important, and you can actually draw axis which is of concentration, and depending upon what concentration you are looking at, you can look at problems on algal blooms to the problems of bioconvection, and if you go in dense enough regime, you might, but not well studied, enter into the regime of what most of the people here think as active matter. So let's just try to see the concentration axis. If the number of organisms per centimeter cube is less than 10 raised to 4, which situation you are in? You are thinking of lakes, oceans, and you are thinking of typical plankton blooms. There are these beautiful satellite pictures that many of you might have seen of harmful algal blooms at various lakes and oceans. We have studied this problem long time ago, and in this particular regime, these organisms are just passively advected by the flow. You need not, because the concentrations are so small, you need not worry about the flow turbulence intensities are large enough, you can ignore gravity. You can also ignore the fact that these organisms themselves are generating flows, and then, but just because of the fact that they try to reorient with the local vorticity and have some swimming capability which points upwards, you can start to see this patchy behavior. Various people have looked at it. Then comes this intermediate regime where many people have looked at collective motions of these organisms in lab settings. In this regime, the initial work which was done by Kessler, as I mentioned, this predates the terminology active matter the way we use it, right? So what is important here is that the cell diameter again is 10 micrometers, it's this, but if you take this as the cell diameter, you can very easily convince yourself that the typical separation between the cells is roughly 2 to 50 times their body length. Now why that is important? Because remember I told you that these cells swim. Because these cells are swimming and they are contractile swimmers, immediately you would say that look, they are generating flows which are, or they are generating stresses which are active stresses, and if you have active stresses in a force-free swimmer like this, you will have a velocity field which decays like 1 over r square. But remember, there is also gravity. Because there is gravity, these guys also have drag, and there is also stresslet. The stresslet decays much more slower than the way the active stress decay. And remember, their cell separation is quite far away from each other. Therefore, for what we are going to talk about today, we are going to ignore active stress. And this has been somehow over the last few years a theme which I am working on, where we look at systems which belong to active matter, where activity is coming through self-propulsion of the organisms, and the active stresses are not so important. And this turns out to be another such system where the gravity or the stresslet is the dominant contribution, and you can again ignore the active stresses. And what I am going to tell you, or rather convince you, that just because of the gravity and the swimming motility of the organisms, you are going to observe all these patterns, right? That's the idea of the talk, and what is the role of the confinement. I won't talk about this particular regime, and we have started to work on it, but that's maybe for some time later. So now how you are going to model such a system, right? That's the next important thing. The model is very, very easy. Remember, I'm thinking of a fluid in which you have microorganisms. Fluid is a Newtonian fluid. These organisms typically live in water, right? So Navier-Stokes equation is a model of the fluid. And remember, these organisms are bottom heavy. So there should be a buoyancy force because of the settling of the organisms. That's put in over here. It's the number density times the volume of the organism times the density difference of the organisms with the ambient fluid times the direction of the gravity. So that's the Navier-Stokes equation. And then there are two ways, and this is again something which was talked about yesterday, how you typically model organisms or a collection of organisms. And you could start to work at the microscopic level, where you try to determine the dynamics of individual organism, or you work at a macroscopic level, where you say, oh look, can I write down a field theory, right? And there was an interesting talk yesterday where one was trying to use the methods in field theory to start from microscopics to get to what is the correct macroscopic behavior. So we'll see whether we could do something like that here, or whether people have already did something like this, at least in this system. So the organisms are the dynamics is very easy. The velocity of the organisms is nothing but the velocity of the fluid at the position of the organism plus the swimming velocity of the organism itself. That's what one typically uses. And remember, the orientation of the organism, I already told you what the equation is, right? We discussed it. How does a single organism swims about? And of course, there is slight rotational diffusivity, but that's all right. Now, another thing you should keep in mind is that, remember, I already told you that we are working in dilute regime. How dilute? That the organism-organism interaction is irrelevant and the active stresses are irrelevant. Therefore, you don't see any contribution here coming out from active stresses or organism-organism interaction. All right, so you can do this, or you can write down the equations or mathematical model in a continuum framework. Now, the Navier-Stokes part, of course, was continuum, nothing changes there. But if you follow any literature on active matter, you would realize that what you would be required to do is, starting from this Lagrangian picture, you could have write down the single particle Fokker-Planck equation and then start to look at moments of the Fokker-Planck equation. And as Satya was pointing out yesterday, then you would have equation for density, orientation, second moment of orientation, third moment of, and you would have a hierarchy, right? And here, somehow I am writing two equations. So what magic was done over here? The magic was that Martin and others, Pedley and all those people long time ago, in 90s itself, when they were looking at this problem, they realized that if you start by writing the Fokker-Planck equation and noting that you are in the dilute regime, you could use what is commonly used in fluid dynamics a lot, that start from the Fokker-Planck equation, ask what is the equation for the number density, and use the generalized Taylor dispersion theory put forth by Brenner and others to figure out what would be the correction to the velocity because of the swimming. So you would have in the normal active matter term here Vs times P, where P is the average orientation of the organism. So if you use Taylor dispersion theory, you can predict how does that average orientation depends on the local vorticity, and that's what these guys did. Similarly, you can predict how does the local diffusivity, now diffusivity is not a number but rather a tensor which depends on the vorticity. So how does the local diffusivity itself depend on the vorticity? And that's fantastic, because instead of working with a hierarchy, You have now reduced the problem into just a problem of working with a number density, although the number density itself, all the coefficients itself, now depends upon the gradients of the flows, right? And what they did quite spectacularly well was that all these guys who are applied mathematicians also doing experiments took out a single organism, put them in various shear flows and asked, can we measure the exact dependence of velocity on the rotation or on the local vorticity and this diffusivity tensor and do a fitting, and at least for Climadomonas, variety of Climadomonas, they have a very weird but still something that you can write down form for how does the velocity depends on the local vorticity, and these are nasty coefficients. No need to worry about what are the exact numbers, but just this is to emphasize that people have beaten this problem to death when you are looking at an isolated swimmer, so you have good handle on what are all these numbers. Of course, you could question the following thing, that the moment I switch on the gravity, all these things could go out of the window, because these equations, the equation for the number density is derived for a simple shear or extensional flow, and how does the single organism is responding to it, right? So when I put in gravity, maybe it works, maybe it does not work. Nevertheless, there are few things important to look at in this mess. First, this velocity, which would be Vs times P, the local orientation if you are working with full equations, when you write it in terms of local vorticity, it is not symmetric. That is the velocity. So x here denotes the downward flow. So remember, the organisms are trying to align themselves in the direction upward, because u is minus Vsp, and if you take a leading order term, which is a constant. So if I look at the organism velocity here, which comes in the vertical direction, it doesn't feel the vorticity, whereas in the horizontal direction, at the leading order, it feels the vorticity, right? So that's very interesting. It correctly is picking out that it was, if there was no flow and if you had randomly oriented organism, it would turn and move upward, all right? So that's quite cool, and similar analysis can be also done for the diffusivity. So you have now a much more simpler system, and you have a continuum equation where you have coefficients where you are finding explicitly tuned based on some experimental results, or you could do a Lagrangian simulation also. And the first thing that we wanted to know, question?
Because the form of D
yes.
tells you that this can only really hold if there is a global extensional axis, right? Because the
of
D
course,
is
yes.
symmetric and it has the same entries, because otherwise there is no anisotropy. And what is sigma?
Sigma is omega by omega is the vorticity, so it's normalized vorticity, no?
Right.
So no, so the point is the following, that I'm looking at a system and there is gravity, right? So these in this particular setting, when they derive this equation, as I pointed out earlier, you assume simple flows. So it could be a shear. So once you say there is an organism in a simple flow, and then you say that there are then collection of many such organisms, how does then the probability density evolves? And that would give you an equation for the number density, no? So that's all that is. Yes. So they are not modifying that. That's why I said that in the limit in which this theory has been developed, you could very quickly question me whether it's valid or not, because I have added this term, and once you have the gravity, the stresslet also present in the system, this equations could go back. But we'll see how good this approximation is. I mean, one of the reasons to go ahead with this is that in turbulence we do these kind of approximations quite often, and they work fairly well. So okay, so what are the consequences of these equations? So whenever one thinks of consequences, let's think of experiment. So this was the experiment which was done by Kessler, which is quite cool experiment. You have a flow which is downflow here, so it's a U2, and so what you have is flow downwards here and upwards here, and then you have put in these microorganisms inside, and what happens immediately is the following, that remember there is gradient here, there is a negative gradient here, positive gradient here. So if I am a microorganism here, I see a vorticity which wants to turn me inside. Similarly, if I am organism over here, it also wants to turn me inside, and because of this you would see a flow focusing. So the organisms would try to go towards the center line of the Poiseuille flow. On the other hand, in the upflow region, what's going to happen is if I am organism over here, I will tilt away from the center line. Same over here. So what would happen is all the organisms go towards the walls, right? And this is what is observed in the experiments, that you have flow focusing here, and here organisms go towards the walls. But something more impressive happens is that if one looks at now these things way more carefully, you have secondary instability presence in the system, where these flow focused stream also makes blip like instabilities. There are regions where you have dense concentration of organisms and few organisms and things like that. And then when they go closer to the walls, it seems as if their concentration grows to some critical concentration and then they fall off. So you have organisms all close to the wall and then also peeling off and then falling down when as a collective their concentration becomes large enough such that gravity becomes important, right? So this is the first effect, and for which you can very easily explain it. Of course, secondary instabilities you can't explain in such a qualitative way. But then, like a good active matter practitioner, you could ask a very simple question. That remember, if I take all these organisms, again dilute, and I ask the following thing, that the following base state, u is equal to 0, all the organisms are swimming upwards, is the solution of the underlying equation. Alright? Question, is this state stable or unstable? And now again, you can do a very simple hand waving argument where you see that, look, what's going to happen is that imagine there is a teeny tiny perturbation, so that in some regions you have fewer organisms, there are some regions where you have more organisms. And now remember, if that is the case, there is gravity. The region where there are more organisms, they will sink. Region where there are less organisms, they will still go up, because you have to conserve the total momentum in the system. And now something funny happens. That means that just by a small perturbation you set up a flow, a shear flow. Oh, but if you set up a shear flow, what's going to happen? If you have a flow like this, I already told you there is a flow focusing happening automatically. More organisms will come down here, less organisms will be here, and there would be an instability therefore. Alright, so straight away, just by gravity in these organisms, you have a flow instability, which tells you that you cannot have a collective flock going upwards like so, rather you would have immediately this thing going unstable. Alright. The next thing you can do is ask, is this the only instability? Remember, the experiments are done in a confined geometry, there is nothing unbounded in an experiment. So there are walls, but again these organisms love to swim upwards. If these organisms love to swim upwards, what they would do is they would have a dense layer of cells at the top. And then again, if you have some perturbation, you would set up flows, and these flows can generate large densities which then peel down like plumes as it happens in thermal convection. So the mechanism is different, but if you look at the flow structure, you would feel as if you are looking at an experiment of thermal convection, and then you have what is known as the overturning instability. Alright, so all these things were known at some level, and I've given you, let's say, a head start with what one observed at least in the early days, or with a very simple analysis. More recently, people have started to look at this system in much more details by doing detailed stability analysis, alright, of these equations in geometries like vertical pipe or channels. And what they find it is quite remarkable, that if you have confinement, it leads to dramatic effect, in the sense that you could have different kind of bifurcations leading to flows where you have organisms concentrating at the center line and also away from the center line, variety of flow states, or you could also explain these various instabilities in the system, alright, and you can even characterize them very, very precisely. What Martin did was very interesting, is that he started to look at the dynamics of these organisms in a very thin Haley-Shaw setup, and what he started to see is that when the plumes form, they are not always at the center line, actually sometimes they get formed very close to the walls. And then the question was, why is this happening? Because when people were doing linear stability analysis, they always assume an axis of symmetry, so you are not going to figure out whether you have anything which can be asymmetric in nature. And the question, many people typically ignore this by saying that, oh, such a behavior is happening because these organisms are also phototactic, which means they are sensitive to light. right? So then if something is sensitive to light, it will migrate towards one of the walls. But then we started to look at this question in a bit more detail. And then we asked ourselves the question that let's, oops, take a very simple setup. You have two walls, you have organisms which are swimming upward, and ask what is the steady state first in absence of any external imposed flow, and also ask the question whether, you see, all the theories or all the stability analysis was done using a Eulerian framework. If I want to do simulation, I can also do a Lagrangian framework. So whether the Eulerian and Lagrangian framework agrees. So that was the starting point of our study. And this is the first thing we did. We assumed that the system is homogeneous along y direction, and I just want to understand what are the inhomogeneities if I solve this equation that are developed along the x direction, right. So if you do the simulation, you quickly see first that starting from a homogeneous state, there is an instability that forms, and that instability eventually becomes asymmetric spontaneously, right. And the question was, all right, that's quite interesting, because now we are getting a solution which is not a symmetric solution. The initial instability was symmetric, but as if I wait for a long time, I get a solution which is asymmetric. Now this is numerical. Can we do something analytical? Is there a structure inside the system which can allow me to classify all these solutions? So turned out fortunately that I could do that, and the idea was very simple, that if you look for homogeneous solutions and impose steady state, then these equations, the ones I told you, simplify to something which is still daunting, but it's much more nicer or easier because the time part is gone. And then you impose weak flow approximation, and then these two equations you can further simplify into equation which looks to have something like a Hamiltonian structure to it. And then what you do is you make some simple transformations which are done here, and okay, one could do this in view of time, I won't worry too much about it, but what you end up with a differential equation of this kind where the coefficient C can be explicitly determined, okay, based on your flow parameters and everything, what is the pressure gradient. And I mean, one could have done without it, but if you look, at least I looked at the literature, and it turns out that this is nothing but a quadratic linear type equations, and these equations allow for a first integral. You can also map it onto a Hamiltonian system to figure out that there is indeed a conserved quantity. The first integral has this form where there is only one unknown parameter, which is k, which is the constant of motion. And so if you do a stability analysis, it's trivial to show that you have a fixed point at origin, okay, and then you have concentric orbits, and these concentric orbits are bound by a separatrix which is given by this k. And what solution that we got, you can plot it here in terms of this phase space of v and dv by dy. The dots are the numerical data and the continuous line is the theory. So it looks like whatever we are doing is not so bad, things are indeed consistent. Now you could ask the following question, that if you are doing numerics, you can do many more things very easily, right, because numerics are way easier than experiments. You can impose a symmetry, and if you impose symmetry, then you can find symmetric solutions again with no flow, where you have a jet, a downward, so positive u unfortunately is downward flow, so you have downward flow at the center, and therefore organisms cluster over here, and two jets, counter jets going upwards, no organisms in this direction. Or you have flows where there is downward flows close to the wall and a central jet going upwards, and wherever there is a downward flow, the organisms will cluster, and indeed all these solutions satisfy these first integral. So that was very nice that we were able to figure out an underlying integral in the equation. Not only that, then you can play the game of asking what happens if you impose an external flow. What happens to the asymmetry of the solution? So what turns out that as you crank up the flow intensity, the solution starts to go more and more towards the center line. If you impose a flow which is, yeah.
5 minutes.
Oh, I have 5 minutes, wow. So let me skip this part, if one is interested I can talk later. But what is crucial part is the following, that you could now compare the Lagrangian and Eulerian simulations, and if you compare the two, they fall on top of each other. So that implies that the simple approximation I mean, you have to spend some time to get to that equation. But if you do that, that works very well, and the Lagrangian picture within error bars work fantastically well with Eulerian picture. But one could very quickly criticize by saying, look, all this is crazy, you're doing things in one dimension. Well, you can do it in two dimensions. And the moment you do it in two dimensions, you start to see these blip instabilities. Above is the Lagrangian picture, below is the Eulerian picture. They agree fantastically well. And you also see spontaneously asymmetric solutions emerging in the system. Turns out that asymmetric solutions are more stable than the symmetric solutions. I won't talk about it. But if you then go back to the experiment and ask what happens if I increase the flow rate, if you increase the flow rate, then similar to experiment, you start to see blip-like patterns appearing in the system. You can again do a theoretical analysis to understand it. You also, if you have a flow which is going opposite direction, similar to experiments, you see that first things accumulating near the wall. That's not surprising. But what is interesting is that the simple physics is able to capture also the fact that you would have now locally densities becoming large enough such that they peel out from the walls, exactly like in experiment. So in experiment there was no approximation. In the theoretical analysis there was this very interesting approximations that one made where one is ignoring the flows, the flows generated because of the individual organism. Still you are able to capture all the features of an experiment, and then we got very happy. We said, aha, everything is working. Let's do something which is even more impressive. So what is even more impressive is that Martin had this very nice Hilly-Shaw setup where you have now confinement in all directions, right? Earlier I was looking at confinement only in one direction. Now we have wall at top, wall at bottom, and also horizontal confinement. And that's interesting. Why? Because remember, wall at sides will give you asymmetry. But if you have also confinement in the other direction, that when something hits the bottom, it will start to see all the walls, and you could have then more crazy behavior. Let's see what happens in an experiment. So in an experiment, they stir it initially slightly, and then you have these plumes forming. And then these plumes stay put. They're not moving that much. So you have plumes, and the plumes are what is referred to in the bioconvection literature as bottom standing. That is, they are not moving around much, like in thermal convection. All right. And now you ask, can I understand this? At least qualitatively. So we said that, look, okay, how do I model confinement? And the answer to that in the other direction, and the answer to that was, as a good physicist, I would use a linear drag model. It works. If you use a linear drag model and you go on increasing the drag coefficient, you start to see something interesting, that at zero drag, you have something which looks very turbulence-like. When you increase the drag coefficient, similar to experiment, you start to see plumes which are very, very stable. However, we are not able to capture the bottom standing plumes which are present in the system. In the experiment, if you increase the confinement more, the bottom standing plumes stop at much earlier level. That's what we observe in the simulations also. However, in all the cases, we are not able to capture the bottom standing nature of the plume, and that we believe is because of the three-dimensional nature of the problem, for which we are still doing some analysis and trying to set up some more simulations. So what I hope I have been able to convince you is that confinement is important. Even when active stresses are not present in the system, when organisms can swim and they have other mechanical properties in them, they can do extremely interesting behavior, right, which is worth looking at. And all the things that we have done, it correctly captures many features away from the walls correctly, but when you are close to the wall, there are still open questions present. And indeed, in the plumes that were forming, it's not at all clear whether the cell concentrations have become large enough that one can still ignore active stresses. So that's another thing that we are investigating now. So with that, I would like to stop and be happy for any questions. Yeah.
Any question? So I was wondering, when you keep increasing the density, you said, I'm not going to say anything about turbulence, but up to what point you can go increase the density before you really have to take into account the interaction?
Yeah, so we believe, this is why I showed this picture. We believe it's somewhere here. So if you go to something like 10 raised to 8 to 10 raised to 9 cells per centimeter cube, beyond that, at least for this organism, it looks like that the active stresses would start to become important. And remember, even 10 raised to 8 is not so large. You're talking of volume fractions. So this regime are volume fractions like 0.01, 0.1%.
This regime is the one you are in.
Yeah, that's 0.1. The oceanic flows are even lower. That's 0, right? So the regime which most people work in, it's much more denser than that. So, really if you're 10 raised to 9, 10 raised to 10 cells per, and that you can do mostly in labs. In oceans or in general settings, it's, I don't know where, maybe in dense colonies or epithelial tissues, there it's of course obvious, but in these swimming organisms, it's not so clear to me.
Okay, thank you.
Prasad, I didn't really follow the last part. These plumes you said, right? These are not because of the gravity or the fall?
No, so they are because of the gravity.
They're coming and settling down.
Yeah, but the fact that they settle down and keep on standing there, it's not obvious why.
The entire stretch.
The entire stretch. It just sits there. Right? So if you see the movie, so with all these crazy flows generated, it's not very obvious what's happening at the very bottom, that these structures, you see organism peel off, go up, but this plume lives for a fairly long time. Why?
What is the reason you say?
I don't know. I mean, at least with the drag you can get it, but there's still, there are obvious things which we don't understand because the other, so what is the dimension C? The width, that is this confinement direction, is only 1 millimeter. So it's really extremely confined system, and then approximating it with a linear drag, is it a good idea or not? We are exploring all that stuff right now.
Okay, so let's think. Oh, we have another question.
So after mapping your model onto the Hamiltonian system, do you have only do you have a fixed point in the top?
Yeah. The fixed point is origin.
Origin.
Yeah, so it's exactly like a Hamiltonian system, right? Where you would have a fixed point and then you have concentric.
Yes.
Yeah, but it's just that those structures are a bit more complicated.